I'm Anil Kumar. Welcome to my series on pre-calculus. In this video, we have taken up 5 very important equations. We'll discuss how to solve absolute function equation. We'll discuss how to work with radical equations, exponential, logarithmic, and trigonometric equations. So one example of each will kind of give you a review of what you did earlier on these topics, and these are very important topics for calculus. So let's begin with the very first equation. You can always pause the video, answer these questions, and then look into my suggestions. So the very first equation is based on absolute function. Now whenever we talk about absolute function, here we have a very simple absolute function, which is absolute value of x. Now this could be written as a piecewise function, correct? So absolute value of x is equal to x for the value of x being greater than or equal to 0, but it is negative of x when x is less than 0. Now this part is most of the time forgotten, and that makes huge errors in many problem solving cases. So remember this, and that really implies that any absolute value function when involved in an equation should be treated as a piecewise function, and therefore we should be really solving this in two intervals. One interval being x greater than or equal to 0, the other one being x less than 0. Now if x is less than 0, in that case we just saw here that the absolute value of x should be equal to minus x, and in this case the absolute value of x should be equal to positive x. So we'll replace absolute value of x with these values and solve the equations. So the first, we'll see what happens on the left side of 0. So we get 3x plus 5 minus 2 times absolute value of x is minus x equals to 3. And on the right side, where x is greater than or equal to 0, it remains at positive x. So we could write this as 3x plus 5 minus 2 times x equals to 3, correct? Now let's solve this. So we have this as 3x plus 5. That gives you plus 2x is equal to 3. So 3 plus 2 is 5x. We can take this 5 to the right side is equals to 3 minus 5. Or we get 5x is equal to minus 2, or x is equals to minus 2 over 5. Now minus 2 over 5 is in this interval, right? So we're talking about, let us say, a number line, right? So we are talking about a number line where we are interested in values on either side of 0. So here we get a value which is minus 2 over 5. So that becomes a solution for us, right? So that is indeed a solution, since it is on the left side of 0, correct? So that is a valid solution. Now let's solve the right side where x is greater than or equal to 0. So we get here as 3x, this is minus 2x equals to 3 minus 5, and 3x minus 2x is x, so we get x equals to minus 2. Now x equals to minus 2 is not a valid solution, right? This is not valid. What is the reason? Well, we are looking into the value of x which is in the domain where x should be greater than or equal to 0. Minus 2 is not greater than or equal to 0. Therefore, this is not a valid solution. So in this particular case, we have only one answer, and our answer is that x is equal to minus 2 over 5. Is that clear to you? Now, some of you can verify both these solutions. If you substitute minus 2 here, you will not get 3 on calculating the left side. But if you substitute minus 2 over 5, you will get 3 as your answer. So that could be a check which you can perform. But I hope you got the concept that whenever you have an absolute function, you should treat it as a piecewise function as shown here. Now let's take the second example, which is involving square roots of square roots. Now these could be very tricky. To solve them, we will actually square both sides. Now, since both are positive quantities, we can square both sides, right? So, without having any error. So, when you square, you get 4 plus 7 square root x as equal to, squaring this will mean what? Well, this means, let me add the step here. What we are doing here is, okay, we'll do it in 2 steps. We have this here, right? And we have square root of x plus 2. So what we're doing is, we are squaring both sides. So when you square, you get 4 plus 7 square root x on the left side. What do you get on the right side? Remember the formula? A plus b whole square. So a plus b whole square is basically a square plus 2ab plus b square. So what we get here is a square, which is x, plus 2ab, that means 4 square root x, plus b square, which is 4. Now let's bring the terms together. So what we get here is bringing the square root of x on this side, let's say. So we'll get here, either side you can work, right? So we have 4 plus 7 square root x minus x minus 4 square root x minus 4 equals to 0. Now 4 minus 4 is 0. 7 square root x minus 4 square root x is 3 square root x. So we get 3 square root x minus x equals to 0. Now how do we solve this? Well, we can take square root x common, right? So if you take square root x common, we get 3 minus square root x. Perfect. We get 3 minus square root x. Now this gives us 2 solutions. One, of course, is that square root of x equals to 0. That gives you x equals to 0. This is a valid solution. Once you put x as 0 here, right, in that case you get 4 square root 2, and here you get 2. So both are 2, right? So that is a valid solution. The other solution is that square root of x is equal to 3, right? So that is the other solution. That really means that x is equal to square of 3, which is 9. Clear? Now whenever you have a square root function, it is a good process to check, right? So it's a good way to check your solution. So we'll check by substituting these values. We have already seen with 0 it works, right? So when you do square root of 4 plus 7 times square root of 0, right, and other side is square root of 0 plus 2, we know both are equal to 2, right? 4 square root 2 and 2. Now with 9, let us see what happens. So square root of 4 plus 7 square root 9 is 4 plus 7 times 3, right? Square root of 9, correct? Which is 25 square root, which is equal to 5. On the right side, if I have square root of 9 plus 2, I get 3 plus 2, which is also equal to 5. So we see both are equal, and therefore both are the correct solutions. So this is our solution set for question number 2. Is that clear to you? Perfect. Now let's move on and take question number 3. So I'd like you to pause the video now and try this question. It is indeed a very difficult question. So we have exponential equation where the bases are all different. Now how could we do it? Well, let's rearrange this. So we get 3 to the power of x times 7 to the power of minus x equals to 5 to the power of 1 minus x. Now we can take log both sides, right? So let's take natural log both sides, which is ln. So we can take ln 3 to the power of x times 7 to the power of minus x equals to ln 5 to the power of 1 minus x. Now using the properties of logarithms, this is the product. So I could write this as ln 3 to the power of x plus ln 7 to the power of minus x equals to, using the power rule, I can write this as 1 minus x ln 5. Now again, let's apply the power rule here also. So we get, in this particular case, x ln 3, and this is minus x ln 7, is equal to, let's open this bracket, we have ln 5 minus x ln 5. Now taking all these x terms on the left side, we get x ln 3 minus x ln 7, and that is plus x ln 5 equals to ln 5, correct? Now x is common, so we get here ln 3 minus ln 7 plus ln 5, correct, equals to ln 5. Now here you can apply the properties of logarithms. When you have minus, it gets divided. When it is plus, it gets multiplied. So we get this as x ln 3 times 5, which is 15, divided by 7 equals to ln 5, correct? And from here we get the value of x as ln 5 divided by ln 15 by 7, correct? So that becomes our solution for the given equation. So I hope the steps are absolutely clear. So when you have such exponential equations where the base is different, you may try to take logarithms on both the sides and then solve them as we have done in this particular example. Now let's take question number 4, which is logarithmic equation. Now we have log to the base 5 of x minus 4 times log to the base x of 5 equals to 4. Now how are they related? Well, let's do change of base formula, right? If I have log to the base a of x, I could change the base to log to the base b of x over log to the base b of a, right? Correct? So that is how you can actually change the base. Well, you could also change the base to x itself, right? We could also write this as, let me rewrite this, log to the base a of x. Let's change the base to x. In that case, we get log to the base x of x over log to the base x of a. So what do you notice here? Well, that is 1. So we get 1 over log to the base x of a. So it's kind of a reciprocal. Do you see that? So this is a very important property of logarithms which we can utilize here. So we can rewrite our equation as log to the base 5 of x minus 4 over log to the base 5 of x, right? This is a reciprocal, right? Just as we showed here. Now let's multiply by log to the base 5 of x. So we get log to the base 5 of x whole square minus 4 equals to 4 times log to the base 5 of x. Clear? Now that is kind of a quadratic equation. We have log to the base 5 of x whole square, and this is minus 4 log to the base 5 of x, and that is minus 4 equals to 0. Well, looking into quadratic equation, it becomes a perfect square. We could factor and write this as log to the base 5 of x minus, this should have been plus, right? So there's something wrong here. So what we get here is, let me just correct this question, right? So this was actually positive. Let me just change this value. This was actually positive, right? Otherwise, we'll not have a solution to this, right? Easy solution, I mean. So let me take this as positive, okay? So we'll make this positive. So I made this change here. Now, this becomes a perfect square, log to the base 5 of x minus 2 whole square. And that is equal to 0. Now that gives you an idea that only it is possible only if log to the base 5 of x is equal to 2. So we have a solution here which is log to the base 5 of x is equal to 2. Now that implies that x is equals to 5 square, right? Which is x is equals to 25 is the solution. Okay, so that becomes our answer. So once again, let me do this correction in the very first page. So the question here was not really typed correctly. So what we will do here is change this question to positive. Okay, so now that is the question which we are solving, and the solution was x equals to 25. Is that clear to you, right? So this 4 gets multiplied with log to the base 5 of x, and when you bring it to the left side, it becomes negative. However, this was positive 4, correct? Okay. Now let's move on and take the last question, which is question number 5. We need to solve the equation 2 sine 3x minus 1 equals to 0 within this interval, which is 0 to 2 pi, right? That's the interval. Now, let's rearrange. So we have 2 sine 3x minus 1 equals to 0. I could write this as 2 sine 3x equals to 1, or sine 3x equals to half, right? So that is what it is. Now remember, we are doing within the interval of 0 to 2 pi. That means x is between 0 to 2 pi. How about 3x? 3x will be between 0 to 6 pi, right? So we have to get all the solutions within the interval 0 to 6 pi. That is important. Second, we have sine 3x equals to half. That basically means we are looking for the solutions within quadrant 1 and in quadrant 2. In both these quadrants, we'll have sine 3x as positive. Clear? To find these values, we can use a special triangle, right? 30, 60, 90 triangle, or pi by 3, pi by 6 triangle. So in this right angle triangle, we have the sides as 1, 2, square root of 3, where this side is pi by 3. So sine pi by 3 is indeed half. Correct? Sine pi by 3 is indeed half, but we have to look for solutions between 0 to 6 pi. So the two values will be kind of like this, right? So we have pi by 6, and the other value here is 5 pi by 6. Now this is within 0 to 2 pi. Now these values repeat after every 2 pi, correct? Correct? So we can have the solutions as 3x is equal to pi by 6, then it'll be 5 pi by 6, and then add 2 pi. Now when you add 2 pi, then 2 pi is kind of equal to, we are talking in terms of 6, right? 12 pi by 6, right? So add 12 to these, so we get 13 pi by 6, right? And 12 to this, 17 pi by 6. So that means the second round, and now another round we have to go, right? So add 12 more, right? So which is 24, 24. So which is 25 pi by 6 and 29 pi by 6. Do you get the idea? So it is important to understand that when the domain is like sine 3x, then the restriction which was given to 0 to 2 pi has to be treated as 0 to 6 pi for 3x. Correct? So the solution now is x equals to, you divide all of them by 3. So we get pi by 18, 5 pi by 18, 13 pi by 18, 17 pi by 18, 25 pi by 18, and 29 pi by 18. So we have 1, 2, 3, 4, 5, 6 solutions, not just 2. So that is kind of important to understand. Perfect. So with this, we kind of come to an end of our series on looking into questions which will help you to perform better in calculus, rather getting ready for calculus. Therefore, we're calling this series as pre-calculus. Well, we made a small change here. There was a typing error, but I hope you must have understood the basic concepts of solving such equations. So whenever you have absolute functions, you have to treat them as a piecewise functions. The radical functions, you may square both sides. For exponential functions, you may take logarithms. For logarithmic functions, you may have to use the rules which you have learned for logarithms. For trigonometric functions, it is important to consider the domain to provide complete solution. I hope that makes sense. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.